Right. So again, thank you all for coming today. Thank you for the invitation to give this talk. This is the area that I've been working on for a while and pretty passionate about. So today we're going to be talking about wearable vision sensors. My name is Kris Kitani. Again, I'm a associate research professor at Carnegie Mellon University, and actually work on a lot of different projects. So this is just kind of a small subset of the things that my lab is working on. So let's get started. Okay, so as many of you know, a lot of the modern sensing devices are becoming wearable. So GoPro cameras or action cameras have been very popular for many years. There's the kind of third generation rise in AR and VR technologies that's happening now. There are assistive technologies that people are developing, and especially maybe in the US, using wearable cameras it's pretty normal now for safety and security purposes. So as we think about this, as a computer vision engineer and as a researcher, we're starting to see this paradigm shift of the types of data that's being generated from third person. So third person would be, somebody uploading their pictures that they took with their camera, to this first person type of sensing modality. So when this happens, how is research going to change? What are the new topics that are going to arise? So we've been thinking about this in the lab. And we're asking ourselves, how can we use these kinds of devices in the context of understanding human activity? Okay. So in particular, we might have devices like smart glasses, smartphones. You can think of that as a wearable device, right? It's basically in our pockets or our purses all the time. And then smart clothing and smart watches. Okay. And I think as we go forward, there's going to be more and more of these kind of wearable smart X that are going to be coming out, right? So we call this domain of sensing first person sensing because the sensors themselves are on the user. Okay, so I'm going to be talking about some of the recent work that we've done at our lab for each of these areas. So what can we do with a head-mounted camera? We'll talk about pose estimation in particular. I won't be talking about using the smartphone IMUs for positioning, but this is kind of a new and exciting area where we're bringing together machine learning with IMU signals to get very, very accurate localization using just a smartphone. Just a plug for that is, in the past, this has been very hard to do because of the drift that you get from IMU because it's so noisy. But recent methods have shown that you can get really good localization if you use learning-based methods. The next paradigm I'll talk about is these chest-mounted cameras for pose estimation. And then I'll also talk about how smart watches and smart watches with cameras, how they can be used for understanding a person's hand pose and how they're using their hand. All right, so let's jump right into this. So I'll start with this idea of using a smartwatch camera for understanding how humans use their hands. So this is a work from UIST 2020. If you want to see more of the details, it's called backhand pose. So the motivation here is that if we want to understand human activity, human behavior, a really essential aspect of that is to understand how people are using their hands. But detecting hand motion is very difficult, especially in the wild in these using a wearable sensor. So our goal is to enable accurate hand pose estimation using a smartwatch camera or a camera that's attached to the wrist, where the fingers are typically not visible, because if you put a camera right on the wrist, it's going to be looking at the back of the hand mostly. And the key idea here is that we think that the deformation of the skin on the back of the hand has enough information to estimate the full 3D pose of the hand. Okay. So really jumping right into this, we're taking a learning-based method, but let me kind of step you through the model that we converged on. So the input is going to be a sequence of images. We have an auto encoder that's going to be extracting some deep features. And then we also have from the hand image sequence, a stack of motion history images. So this is something that was developed, I think, in the 90s. It's basically doing temporal differencing of images and using that as an input. Now, those hand images and the motion history images are going through ResNet 18. We're concatenating them and then passing them on to an LSTM. So it's a recurrent neural network that's looking at a stream of images coming in. Okay. What we're trying to predict, remember, is the 3D pose, right, of the hand. So where are all the joints? How are they moving over time? We have a Kalman filter that's going to be acting on the output of the LSTM. And then we also have a residual that we're passing on, and the output of the Kalman filter and the residual of the LSTM feature is being merged, again, put through a multi-layer perceptron. And the output is going to be 19 different joint positions and their angles to describe the joints on hand. Okay. Further, for a visualization, we take those key points. We have inverse kinematics to solve for what the hand might look like, and then we visualize it using some computer graphics. All right. So that's the basic underlying model. Again, more details are in the paper. But let me show you some demo videos of how this works. So in the top left, what you'll see is a person with moving their fingers around. And then on the screen, you can see the visualization of the pose that's being estimated. All right. On the right, we're showing that this system will also work in indoor dim light. Okay, it can't be absolutely dark, but as long as there's some light, we can still see the back of the hand. So remember, the input to this algorithm is not the dark hand image in the middle, but actually the back of the hand on the right side here. Okay, so sometimes you could see the fingers, but for the most part, it's the back of the hand. And then you can see the estimate there. We have an example of playing on the piano, and then also an example of this algorithm also working out when you have strong sunlight. So that's just to show that the algorithm that we developed has some robustness in terms of the environmental lighting. Okay, so we were able to do this. What might you be able to do with this, right? So here's a possible application. Maybe you can use your hand gestures for controlling the smartwatch. Maybe another application is you have your fingers tapping on a virtual keyboard, and you use that as a new kind of gestural interface when you don't have a keyboard. Maybe you need a mouse, and all you have is your smartwatch with a camera on it. Well, if you can understand the motion of your hand and your fingers, you have a virtual mouse that you can use. This one is a little bit more of a stretch goal of maybe what could be possible. Is we think you could also do object recognition. So if you can understand how the hand is grasping an object, that gives you a lot of information about how big the object is and what shape that object has. And maybe you could use that for object recognition. All right, so we're starting to get some questions. The hand in the real world is left, and then the one on the rendering is right. I'm not sure why it's flipped like that. I think that's just a visualization bug there. Can you use this to determine if someone has pulled a trigger or not? That is a good question. I would think that with the how do I say this? When you're holding an object with a trigger, there's only so much that your hand can do relative to the examples I'm showing here, right, where we have all this free motion. So I would assume that would actually work pretty well. Have you tested this out for different size people? So we have not done a full study on how robust this is, you know, the kind of study that you would need to make this a commercial product. We just tried it on a small group of graduate students. Yep. Okay, so I think it's fairly robust, and with enough data, yes, it should be able to generalize to more people if done properly. Great. So let's move on to this next topic here, which is this chest-mounted camera for pose estimation. This also another paper from UIST 2020 called Mono Eye. Right. The motivation here, again, is that can we use a single chest-mounted camera to continuously monitor human activity and what they're doing with their body? The technical goal here is to accurately estimate the body pose using the chest-mounted camera. And the key insight, or the key idea here, is that if you have a very, very wide angle chest camera, you can actually capture parts of people's arms and legs and their chin. And we could use that information to infer the full 3D body pose. All right. So the method itself, again, is using a learning-based method. It has 3 streams. So input is the chest camera video. One stream is estimating the camera pose. So how is the root or the center of the body moving? Or how's the camera moving? And then the second stream is saying, okay, relative to the root position or the camera center, how is the body pose changing? Where are all the joints? What are all the angles? And then the third stream is focused just on the head. Which way is the head looking in 3D? We bring all of those together and we're able to get a full 3D pose estimate of the person. We also have an interesting application where we can synthesize what the person is looking at, because if you know their head position, you could get a proper cutout, right, from the video to see where they're looking. So some fun applications or might be useful applications later is that you have this wearable camera. Maybe you can use this for sports, right, where you're getting a 3D reconstruction of all the sports players with just one chest camera. So here's a little demo video where you have 2 people walking by each other. One person has the chest camera, and we're doing kind of a reconstruction of soccer there. And then here we have a reconstruction of 3 people like waving at each other, or 2 people waving at each other. So there's a sequence of processing that's happening to make this happen, but that's a possible application. So maybe you could think about, yeah, how this could be used in different scenarios. Okay, let's move on. This is the last part. What can we do with a head-mounted camera? So we're kind of focused here on these VR headsets or AR headsets that have cameras built into them. And again, we're focused on pose estimation. All right. So this is a paper published at NeurIPS last year, and then we have a follow-up work, I think, this year that kind of extends this. But let me explain the basic idea here. So what we have as input is an egocentric camera video feed. So there's one camera on the headsets looking forward. It's capturing the environment around you, but it is a forward-facing camera, so it doesn't capture your body at all. Okay, so we have that as input. What we're going to do from that video is we're going to detect objects in that scene. And then what's going to happen in the video is the person is going to interact with that object. And our goal is to output the full 3D human pose, including our awareness of the objects that are in the scene. Okay, so the input is, again, one single video looking forward. Most of the body is not captured. The output is a full 3D pose estimate of the person wearing the camera. Okay, so what does that look like? Something like this. So the input is on the left. You have an input video, and then we have a reconstruction of what we think that person did on the right. So let me show you a longer video in the next one. So what happens is in this input video, we're observing objects in the scene. The motion of the video itself is telling us how the person's head is moving. And what our model does internally is it tries to estimate the full 3D body pose by validating it inside of a physics simulator. Right? So the algorithm guesses, well, it knows where the head is from the ego motion of the camera. It guesses the full 3D pose. It puts that into a physics simulator and says, is this possible? Is this a physically valid, a possible estimate of what the person is doing? If it passes that test, then we say, okay, this must be what the pose is. So we're kind of hallucinating or guessing what the 3D pose is. Okay. So this technology, I mean, why is this important? You know, in the future, I mean, I don't think we'll be wearing VR headsets, but maybe we do have cameras embedded in our glasses or, you know, chest camera. And if we could estimate what the person is doing, this might be useful for different sports applications, for physical therapy applications. Maybe if you want to do large scale AR or VR or AR, MR, you're going to need these kind of technologies where you can sense what a person is doing, even if you don't have full access to their body. All right, so this is the last slide, just to wrap it up. First person sensing, I think this is something that's going to continue to become more and more important in the way that we understand people. I gave you some very, very early prototype systems of what you can do with a head-mounted camera, chest-mounted camera, or a wrist-mounted camera. And just to as a takeaway for you all, maybe these wearable vision sensors are going to be the next paradigm in human sensing. Where is that going to go? What kind of new technologies are we going to see? I think this is what we're going to have to figure out as researchers. So thank you very much for your time today. That's it.
Awesome. Thanks, Kris. So as you can imagine, you have a boatload of questions in the Q&A. So if you want to chip away at some of those, that would be awesome.
Sure. Okay. So what's the minimum resolution camera do you need? So I guess we haven't run that experiment. We've been using GoPro cameras for most of these experiments. So that'll give you a range of the resolution that we're working with. To keep ethical AI in perspective, would a robust study also include people of different ethnicity and skin color? Yes, of course. And I think one of the questions earlier kind of alluded to that as well, right? Different body sizes, different skin colors, I think would definitely need to be taken into consideration for commercial development. Can the chest-mounted camera be used to know if a person is following you? That's a good question. That is a good question. I would think not, but there might be an interesting way to do that. Yeah. Let's see. Where are we? SME posture. Oh, I see. You're clearing some of the answered questions. It appears to also estimate posture. Yes. So this is something I did kind of mention it, like with physical therapy or let's say like post-stroke rehabilitation. Maybe a sensing system like this can be used to measure how a person is using their body and if their physical function is like changing over time as they're going through therapy. This could be something that's really useful to therapists because usually they can only interact with the people inside like a clinic, right? Running kind of pre-planned activities. So that was a good observation. Let's see. Can you hallucinate or predict what an arm is doing that is out of the field of view? So yes, so that's essentially what we're doing with, especially with the physics simulation, is we try to hallucinate what the limbs are doing, even though we can't see them, and they should be valid in the physics simulator. And if it is, then we say, okay, this is the high probability that this is actually what's happening. So we are hallucinating there. It's like a under constraint problem. Last one. How are these simulated environments generated? Right. So you could use any physics simulator that you want. The way we're generating it is that we're running object detection. In newer methods, we're doing like a 3D reconstruction and then inserting these synthetic objects into the scene. And then we use them when we're running the physics simulation. Yep. So there's, I guess, a whole stream of computer vision work on just scene understanding, scene reconstruction, which could be leveraged. We're not going that deep into it at the moment. Okay. Is the inferencing and computation done on edge device or on the server? So right now, this is, let's see, the wrist watch one, and that one is running in real time, but it is using a computer, like a desktop computer. It does run in real time, so I could conceivably run that on an embedded device. I think the networks are not too heavy. Same with the head-mounted head pose. Yeah, I think all of these could be run in real time on an embedded system. It just we are not running it like that right now. Have you ever thought about predicting the next move of the user instead of just recognizing the motion in the current time step? So yeah, so I actually have a stream of work on trajectory forecasting and activity forecasting, which I didn't talk about today. So we do have a ACCV paper on using a wearable camera. Yeah, ACCV. You also want to check out ICCV 2000. I forget which year, but it was best paper honorable mention on trying to predict what people are doing using a wearable camera. Yeah. Okay, that looks like that's it for the questions.
Kris, I do have one more question. So I think it's really fabulous that this emphasis on moving from third to first person view, but like so much of vision for the last 20, 30 years has been third person view. Like why, what in your view, in your experience so far, what is most different about first person doing computer vision in ego versus exo or third person?
Yeah, so let's see. In terms of differences, I mean, there are differences, but I think instead of mentioning those, what I want to mention is that when we're using a wearable first person camera, we have a much higher resolution video of people with their hands interacting with objects. So this opens up a whole new area of what does it mean to understand people when they're interacting with objects. There's all these topics like what does it mean for an object to change over time, like an object state change? How do people use their hands, right? The different like grasp taxonomies, what are pressure points, like detailed manipulation, all of these. It's actually kind of intersecting with a lot of robotics research. So maybe it's not just that it's different, it's more that it's opening up a whole new world of research topics because of this new perspective that we have. So I think that's what I would emphasize.
So Kris, I think we have one last question in the queue that we may have missed, and it is, can you use this to determine if someone pulled a trigger or not? I'm going to assume this is a trigger to a firearm, perhaps in crime scene reconstruction or something like that.
Yeah, so I think I did answer that one during the talk, but I do think it's possible. Probably a good idea to use some audio with that too, to get the recognition rate up.